let's start over. Again, it's Thursday, October 15th, 2020. We're starting Chapter 2. If you're just joining us, you get the benefit of me making a folly and not sharing my screen, so we're starting over. Hooray! Here we go. So, percentile. This will work much better now that you can see what's going on. Definition of percentile, the piece percentile of a distribution is the value of, with P% of the observations less than it. All right. Percentiles are one way to describe the location of a value within a distribution of a quantitative variable. So again, it lets us say where certain values are within our distribution. So we can kind of expand our descriptions to talk about certain people within a distribution, or observations or objects or things that have occurred more specifically if we need to. So we have an example here. We have this stem plot here, which describes test scores of 25 students. All right. And we're going to look at what percentile is the student who scored an 86. So let's look at this example. Now that you guys can see my screen, it's probably going to work much, much better. That color should work. All right, so we have the 86, right, goes along with this right here, right? We have 8 and 6, so this is the 86 of the score. So to find the percentile, I need to find out how many scores are less than 86, all right? I could count up all the ones less than, but I can see in this distribution that there's much, much fewer scores equal to or greater than 86. So I'm going to count those and subtract that from 25 to find out how many are less than. All right, it's the working more efficiently part. All right, so we have 1, 2, 3, 4 scores of 86 or greater. All right, so we have 25 minus 4. That's going to get me 21. So I have 21 scores less than 86. All right. Scores less than 86. So to calculate the percentile, I'm going to take the 21 and divide it by the number of scores. So we'll get out our calculator, 21 divided by 25, and we get 0.84. Right? So 0.84, and then we convert to a percent by moving our decimal place 2 spots over. Got to convert that. And that is 84%. So 84% of the students scored less than an 86, which means the percentile for the student who scored an 86 is the 84th percentile. Okay. So when you write a percentile, it's not 84%, it's the 84th percentile. 84% is just how many people scored less than. When we talk about the percentile, this is now referring to a location. The 84th percentile. And it means that the student who scored the 86 is 84% of students scored lower than that. All right, so when you get like test scores, it's very common with test scores like SAT or PSAT or any kind of like standardized test. You'll get your results back and they'll tell you what percentile you were in. It's like, oh, you were in the 90th percentile or the 99th percentile or the 87th percentile. You get all these range of numbers. And essentially it means if the higher your percentile, the better you ranked among your peers essentially. Right? If you're in the 95th percentile, that means only 5% of those people who took that same test scored higher, all right, equal to or higher than you, and 95% scored lower. Right? So this is how the percentile gives us a better idea of like where you stand, or where a student stands, or where an observation stands within the entire set of observations. Any questions? Okay. Anna, yes.
I don't, can you explain why you subtracted the 4 from the 25?
Yes, absolutely. So within my data set here, right, I have 25 what we'll call observations, right? Because we have 25 students. Right, so in this stem plot, I have 25. Oh, you cannot see that green over there. Sorry about that. Let's try this. That we can see. There's 25 observations. All right. Now, for the percentile, you know how many scores are less than a certain value, right? So rather than counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, to count all the numbers that were less than 86, I was like, well, I can easily see in this distribution that there's only 4 numbers that are equal to or greater than 86, which was 86, 89, 90, and 93. So rather than count to 21 by counting all the scores less than, I just subtracted how many were greater than from the total amount of scores, which was only 4 scores.
Okay.
Right.
Okay, I got it.
It was a shortcut, essentially. Like
Yeah,
I didn't want to have to count it.
Yeah. Okay. Thank you.
You're welcome. Any other questions? Thank you for asking, Anna. It's excellent. If you don't understand, please always ask. I'm more than happy to explain things. Things that I see and understand don't always come through clearly. So, all right. Does anyone need another moment to write anything down on this screen? Okay. Next screen. Where's my mouse? There it is. Okay. This is a big mouthful of stuff. Bear with me. We'll see an example on the next slide. Cumulative relative frequency graphs. All right. Cumulative relative frequency graphs allow us a graphical way to look at percentiles. Before I read this thing, if you guys remember, most Math 1 teachers use this example in Math 1, and I know it was a long time ago, guys, but you may have seen the same example again in Math 3 of the growth charts of percentiles. And it's these lines that are like between certain values, and you can see what percentile a child is by where they fall in those growth charts. And they use those percentiles very frequently. I know because we have, gosh, what are they? Almost 16-month-olds. And every time we take them to the doctor, they tell us what percentile they fall into for like height, weight, and head size. My son, Grisham, he is in the 80th percentile for height and weight, which means he's bigger than the average kid his same age, but he's not the biggest kid, right? He's the 80th percentile. But these charts, they show you these charts, and it's all about these little curves, and you look at where your kid's data point falls within those curves. So the cumulative relative frequency graphs are those curves that we can use to see where certain values lie in the percentile range. And so we're going to look at how we make those and how they get created. That's what this whole thing is about, at least this part. So to get a cumulative relative frequency, you first need a relative frequency, which is a percentage, then the cumulative frequency, where you add the counts in the frequency column for the current class and all classes with smaller values of the variable. Lastly, find the cumulative relative frequency by dividing the entries in the cumulative frequency column by the total number of individuals and convert to a percent. It's a lot of steps, a lot of things. It's not that terrible if you organize it. Same as when we did the standard deviation calculations by hand, making a table and organizing it helps the whole process go better. So in our next slide, we're going to see a table that shows us, okay, we start here, we do this, we have our cumulative relative frequency, which then allows us to make a graph. So, I know it's a mouthful. Before I move on, I'm going to see, does anyone need some time to write this down if you're adding this crazy paragraph to your notes? Please raise your hand. Excellent. All right. I shall pause and drink some coffee. Oh, I love coffee. Aha. All right, let's see. Okay. All right. We look ready? Let's move on. All right. There's a lot of stuff on this screen. We're going to go through it one piece at a time. So we have the table and the graph represent the ages of the first 44 U.S. presidents when they took office. Here we have our table of values that goes from frequency to relative frequency, cumulative relative frequency. Okay, so we start just with our frequency. This is, the easiest one to have, right? It's just based on counting our data, right? So we have 2 for the age between 40 and 44, 45 to 49 is 7, 50 to 54, 13, 12, 7, and 3. Relative frequency we're familiar with. We've calculated this. We understand that we just take the frequency, and divide it by the total number. Cumulative frequency now is a new thing, and cumulative relative frequency is new. Cumulative, it essentially adds everything up as you go along. So we start with just 2, which is the same for the first class. And then the second class here gets added to the first class. So we have 7 plus 2 is 9. And then 9 plus 13 is 22. 22 plus 12 is 34. 34 plus 7 is 41. 41 plus 3 is 44. When you get to the final class, your cumulative relative frequency should be the total number of observations. In this case, it's 44. If you do not end with the total number of observations, you have made an error in your addition, in your process. You maybe skipped a class on accident or had a typo in your calculator, but that's an easy way to see if you made an error along the way. Then the cumulative relative frequency is found the same way as we found the relative frequency, but it's just based on this cumulative number. So it's this number divided by total number of observations. So again, the very first class should be the same. Right? This one's like the same across the board, right? Frequency is 2, relative frequency is 4.5%, cumulative frequency is 2, relative frequency 4.5%. And then we go to 9 divided by 44, 20.5, which we could also get by taking this relative frequency, 4.5, and adding it to the 15.9. It'll get us close, but if you notice, it's not exact, right? There will be some rounding error if you do it, depending on how you do it, right? The most accurate is simply doing the division. If you're in a rush and you need an estimate, you can use the relative frequencies and add them up as you go along. But again, you may end up with some rounding error. So you just got to be watchful for that. Right, so again, 9 divided by 44, 22, 34, 41, 44. So you should, again, this last value should be 100%. Right, the cumulative relative frequency for the final class should be 100%. If it is not, if it's considerably greater or lower than that, then there's probably an error. If it's 100.1 or 99.9, probably just a rounding error, not a big issue. Okay? So that's how we get this table built up. And we can find all these values. Any questions on how the table and the cumulative relative frequency and cumulative frequency and cumulative relative frequency are found? So then we move to the graph. And this is one of those curves that I was talking about. It's not a straight line. Most of the time it's going to be slightly curved and might curve in more than one direction. That's okay. All right, to make a cumulative relative frequency graph, we need to plot a point corresponding to the cumulative relative frequency in each class at the smallest value of the next class. So for example, for the 40 to 44 class, which is our first class, the point is plotted at a height of 4.5% above the age value of 45, right here. Right. The first data point is 0, right, which is placed at 40, which is the smallest value of the first class. We just get to put 0, right? And this data point means that 4.5% of presidents were inaugurated before they were 45 years old. Right? When we're talking about percentiles, whatever percentile you're at means that you're talking about how many things are smaller than that value. What percentage of things are less than that? So Our class is 40 to 44. All of those numbers are less than 45. So at 45, at 4.5%, the 4.5 percentile, 4.5% of presidents were inaugurated before they were 45 or when they were younger than 45. We can move along here and say the same thing about these other percentiles. And then what this type of graph allows us to do is we can approximate percentiles. So like if someone was 62, we can find approximately where 62 is on the graph, go up to our line, go over, and we can say, okay, well, that's probably like the 85th percentile. Right? So we can start identifying percentiles for specific values using our graph, an estimate. And this is essentially what happens when you're placed on percentile charts. They're using the chart as a guide, and they put your data point in there, and they see where it falls on the chart. Okay, what questions do you have? Okay. Does anyone need another moment to write anything down from this screen? Please raise your hand. All right. Hold on. So, moving on to our last slide here. So another topic, well, related topic. The other thing we're going to talk about today is the standardized score, otherwise known as the Z-score. This relates back to our standard deviation, which we learned more about on Tuesday. So a standardized score, or Z-score, is defined as if X is an observation from the distribution that has a known mean and standard deviation. The standardized score for X is this formula: Z equals X minus the mean divided by the standard deviation. A standardized score is often called a Z-score. All right. So here's what we're going to do. I didn't get this 100% set up. All right. Here we go. So we're going to do an example here, but I need to be more well prepared. Give me a second. Yeah. I'm going to do that thing, that thing. I don't need any suggestions, guys. Thank you. There we go. All right. That's all I need to do. We're going to use the same data set and that score of 86 that we saw earlier. And we're going to do some math. We're going to see what is the standardized score. All right, so let's see. We shall use that color. All right, so we have 25 observations. All right, and we need the mean, and we need the standard deviation. All right, so, easiest way to do this is we're going to get out our trusty calculator and have the lovely graphing calculator do our work for us by adding our data. Let's do that. Bigger. All right, so we're going to go into our stat and edit. And we'll just go to list 5 here because I don't want to clear out the other ones at the moment. And we will get our data put in here. We've got 67 and 72. 4. $25, excellent. All right. So we've got 25 scores in here. They're already sorted from smallest to greatest because that's how we entered them. So we don't have to worry about doing anything like that. Now, we're going to go back to stat. We want to hit calc. I want my one variable statistics, not of list 2, but of list 5. And we're going to calculate. Boom. Excellent. So we have a mean of 80 and a standard deviation of, call it 6.07 as a rounding. All right. So again, I'm looking at this very first entry here, the X bar, that's our mean. The SX is the standard deviation of the sample, which is 6.07, give or take. All right. So that way, let's write this down. We have our X bar equals 80. That is our average score. Our S sub X, which is our standard deviation of the sample. We're rounding to 6.07. Now we have all the information we need. We're using the same observation of 86. So our z-score will equal 86 minus 80 divided by 6.07. Okay. Which will be 86 minus 80. Which gives us a 0.9884678, blah, blah, blah. So we're going to go 0.99 and round to 2 decimal places. So the z-score for a score of 86 on this test is 0.99. Right? That means that essentially the student is 0.99 standard deviations above the mean. So it tells us that the z-score, positive z-score, means that that person's score or that person's observation, whatever you want to call it, is above the mean. A negative z-score, which is possible and will happen, means that that person's observation is below the mean. And the z-score lets us relate that to the standard deviation. And if you remember when we talked about standard deviation on Tuesday, we can use that general rule of if you're 2 standard deviations away from the mean, that could be an outlier. So this allows us to kind of individually see if things are outliers, if that z-score is greater than 2 or less than -2. But it also gives us another way of talking about the location of specific scores in relationship to the mean. Okay? So that's what our z-scores kind of represent. It's called standardizing your scores. And what it does is it relates everything to distance from the mean. We can make graphs of these scores, and it kind of centers around how far from how many standard deviations things are. We'll look at those things later. Okay, we're gonna try something new. Bear with me, guys. I know I'm right up on that like 40-minute mark, but this should be helpful, I hope. Let's see, we'll find out. So I'm gonna end this slideshow. Yes, I wanna keep my annotations. And we're gonna go to, let's see, this one. And we're gonna do this, see what happens. We'll do that. Come on. It's thinking. I want the link. All right, so guys, in the chat, I'm putting a link. Please click on that link. It'll allow you to participate in this little activity to help us get a little more familiarity with percentiles. So when you click on that link, it may ask you to log in. You're logging in with Google, right? Many of you guys are already logging in. Please use your school email and login stuff over a personal one. I believe that works best. We are gonna start. All right, so we're looking at location and percentiles. This is just title screen. So we're using the same stem plot as our previous example. You just need to type in a number. How many students scored below a 72? So find 72 on our stem plot and find how many students are less. All right. Time. All right, so in this stem plot, the only score less than 72 is the 67. So the correct answer was 1. There's only one student below a 67. 67 was the lowest score and the only one less than 72. All right. Any questions on that one? You're going to need it for the next question. Remember, there are one score less than 72. Okay. Next. So if James, a student, scored a 72, what is his percentile? All right. So the correct answer was 4, the 4th percentile. All right, we get this because there is only one score that was less than 72. So we take that number 1, divide it by 25, which will give us 0.04. We move our decimal place 2 spots over to convert that to 4%, which then means that the score of 72 is at the 4th percentile. Okay. Let's try another one. So now we're considering the score of 93. Right. What is the percentile for 93? Alrighty. So the correct answer on this one would have been 96, or the 96th percentile. All right. When we have 24 that scored less than 93 on this test, that means we take 24 and divide it by 25, which gives us 0.96. So we convert that to the percent of 96%. The 96% of students scored less than 93. 4% scored 93 or higher. So that means that the score of 93 is at the 96th percentile. Okay. Try another one. All right. So we have 2 students who scored an 80. What is the percentile for that score? Once again, remember to first consider how many students scored less than 80. All right. So for this question, the correct percentile would be the 48th percentile. 48% of the scores were less than 80. We had 12 scores less than 80. We take 12 divided by 25, that gives us 0.48, which means 48% were less than. So our percentile for the score of 80 is 48th percentile. Lastly, looking at our schedule, our modules, we're on week 8. So there is a discussion board for today having to do with percentiles. All right, so it's going to be very similar to the types of problems we were just working with. And the other thing is our Chapter 1 self-assessment that is available. Right? The suggested due date for this is October 23rd, which is not this Friday, but next Friday. Keep in mind, I would like to get this in before the end of the grading period, which will be on, it's like the first week of November. I think it's the, shoot, I forget. I put it in here. The 6th. Right? November 6th is the next end of grading period. Right? So I'd like it in before that. If it's not in, like I did with the previous one, I'm going to kind of auto grade it to a 1. And because of how much it's weighted, if you get that, it may hurt your grade, right? But once you turn it in, it will get replaced with a more proper grade based on your understanding. Right? Any questions, comments, concerns? Alrighty. I'm going to stop the recording.